Good afternoon, everybody, and welcome to our webinar this afternoon. Before we start, just some housekeeping. If you have any technical issues, please send a short message in the questions box, which you'll find on the right-hand side of your screen. We'll try to help you with those technical issues as best we can. Also, during the webinar, RSSL would like to invite you to ask questions using the same question box, and at the end of the webinar, time permitting, we'll try to answer as many as we can. Any we don't get round to, we will answer offline and share them with you, along with a copy of the slides from today. So today's webinar is the last in our current series and is about the design and qualification of isolators. For those of you that are new to these webinars, my name is Annette Russell and I'm the Sterile and Non-Sterile Microbiology Lead at RSSL. I've worked in the commercial team at RSSL for over 6 years, and my role is to support clients to interact with our technical team to get the best possible experience that they can get. For those of you that are new to RSSL, we are a company based in the Reading area, which is just outside of London, about 40 miles west of London and Heathrow. We've been around for about 30 years and we have about 250 scientists working and supporting clients in over 12 different technical areas, of which microbiology is just one of them. We support our clients globally, and we even have clients in the US and as far away as Singapore and Australia. We are a relatively compact CRO in that our sites are all very close to each other, which means we have a cross-site agility to manage complex multidiscipline projects. And we are lucky to be backed by our multi-billion-dollar parent company, Mondelez, which enables us to have access to funding to support our expansion and growth. Our diversity means that we are able to support a wide range of biological, microbiological, chemical and physical analytical services across all phases of clinical development through to commercial release of your products. We're exceedingly well placed in the area to be able to support the new Annex 1 regulations, of which we've been doing this webinar series. And we're lucky to have a very knowledgeable technical team who can both advise and support you if you have any specific issues. Well, that's enough of me now. I'd like to introduce you to our speaker. I'm sure many of you know or heard of Dr. Tim Sandle and have subscribed to his many publications. Tim has over 25 years of experience of microbiological research, biopharmaceutical processing, and Tim is a member of several editorial boards and has written over 600 book chapters and peer-reviewed papers and technical articles relating to microbiology. Tim works for a pharmaceutical manufacturer in the UK, but also finds time to be a visiting tutor at both the University of Manchester and UCL. I'll now hand you over to Tim.
Okay, thanks very much, Annette. We'll just do the screen swap and go over. So is my screen okay? Has it come through okay, Annette?
Yep, I can see that.
Okay, brilliant. Right, well, welcome everybody. This is the final webinar in the series, as Annette said. So what we've done with this series is continue to sort of deep dive into some of the key topics that appear in the Annex 1 revision, and just a reminder that the new version of Annex 1 is fully implemented, apart from one aspect of freeze dryer loading on I think August the 25th, certainly during August this year. So everything's heading in the right direction. So this webinar is about isolators. Isolators feature fundamentally in Annex 1, and there is a nudge, an encouragement towards the use of barrier technologies, certainly closed RABs and with isolators as well. The earlier draft of Annex 1 was much stronger in favour. The current version, the new version that's coming in, is also very strong, but not quite as strong. There was a potential for isolators to be mandated for aseptic processing. That there's still a wider range of options, but isolators are fundamentally key to reducing contamination control if they are maintained properly, and this is one of the things we'll have a look at. So we'll have a brief introduction to isolators. We'll look at isolator decontamination cycles. We will have a look at the biological indicators and the qualification process. We'll also have a look at some of the key aspects for maintaining isolators and some of the parameters that are worthwhile trending. And we'll do a little bit of a case study around a sterility testing isolator, and many of the fundamentals are the same as for aseptic processing isolator as well. Okay, so let's move on to the isolator concept. So just to bring everyone up to speed, if you're less familiar, an isolator is defined in ISO 14644 Part 7 as a separative device. Maybe that's a slightly limited definition, but an isolator is an arrangement of physical barriers that are integrated so that the workspace forms an enclosed environment, and there is a seal under pressure from the outside environment, and that inner space is subject to decontamination and supplied with clean air. So we have an environment to process or to test in that is designed to be free from contamination. And as I said, we maintain that through a routine sanitization cycle that's subject to validation, and we can carry out a number of confirmatory tests relating to environmental parameters and through environmental monitoring. And most importantly, and this is one of the fundamentals that Annex 1 is getting to, there's an isolation between the operator and the process. So one of the underlying themes of Annex 1 is that grade A is a space without human intervention, and there's certainly one stream of thought that says that you cannot have grade A if you have a person within it. So there's also means to get things sometimes inside and out of the isolator without breaching the isolator environment. Isolators will have the operator interaction through glove ports, or if they're very sophisticated, they will have done away with glove ports entirely and just consist of robotics and automation. Also need this mechanism for transfer, as I mentioned, and for getting waste out as well, which is also very important. Okay, so that's kind of a broad definition of isolators. And in terms of maintaining the barrier, then either we have a solid wall, or there are some examples of flexible wall isolators that they're less common these days, but they were certainly part of that first wave of when isolator technology appeared in the late 1980s. And with the exception of where we are handling products that could cause human harm, so certain medicinal products like cytotoxic drugs, then isolators, when operative, tend to be positive pressure, and that's one of the key contamination control principles. So this is a pressure positive to the room that houses the isolator, and they will be provided by high efficiency particulate air through HEPA filters of EN1822 class H14. And to ensure that the pressure is appropriately maintained, there would normally be pressure alarms and readings. And all isolators to a slight degree will leak air. The important thing is with ensuring the minimisation of leakage, because excess leakage of air could lead to the ingress of air from the surrounding environment, which is going to have a level of contamination. So we need this pressure monitoring, this ability to leak test and assess the isolator integrity, and also inside to be confident that we have HEPA filter integrity. It's also important that there is a rapid airflow inside the isolator. Now, some isolators inside can be designed to be turbulent flow and some are unidirectional airflow. There's always an advantage with unidirectional airflow in being able to sweep contamination away from the critical zone and to expunge that from the isolator more rapidly. And unidirectional airflow has an added advantage if the isolator has glove ports, for when an operator puts their hand inside the glove, then if there is any integrity loss of the glove down to the level of a pinhole leak, then when that hand goes in, there can be this kind of almost like jet stream effect where air can be pushed through and with contamination. So that risk is obviously lessened if there's no holes, but it's also less if there's unidirectional airflow as well. The other key advantage is with the ability to run an automatic decontamination cycle. And there are different chemicals that can be used for that process. Probably the most universally common is hydrogen peroxide, but it's possible to use peracetic acid or chlorine dioxide or even theoretically ozone, but hydrogen peroxide counts for the bulk of the isolator cycles. And isolators are said to disinfect or to sanitize or to bio-decontaminate. They're not said to sterilize. And there's obviously some debate about whether or not isolators can sterilize or not, but in order to maintain compliance, and certainly within the UK, the official position of the MHRA is that isolators do not sterilize, but in fact they sanitize or disinfect, and that's due to hydrogen peroxide not being a penetrative agent, and also to do with some aspects of the fragility of the cycle. There are some others who take a different position, but in order to comply with MHRA wishes, then it's best to avoid the word sterilisation. So the achievement of the required level of sanitisation is achieved through the use of biological indicators. So we're going to have a quick look at hydrogen peroxide, because it is universally the most common agent at the moment. So hydrogen peroxide is a vapor disinfectant, and it employs a free radical mechanism, and this facilitates its microbicidal action. And it is very difficult, if not impossible, for microorganisms to develop any kind of resistance to a free radical attack. But this is dependent upon the vapor reaching the microorganism. So the distribution within the isolator is important. So maintaining concentration, distribution, contact time, and also ensuring that the isolator is clean, because hydrogen peroxide is a poor penetrative agent. So if there is dirt, grease, for example, even down to the level of, say, a fingerprint, then the hydrogen peroxide will struggle to get through that and make contact with the microbial cell, and direct contact with the microbial cell is the fundamental for the oxidative reaction and then the death of that microbial cell. So hydrogen peroxide vapor is typically generated by flash evaporation. So the starting point is typically a 35% weight by weight liquid concentration of hydrogen peroxide. And there is then a process of producing a vapor. It's technically not a gas, but is a vapor, and that's just down to the level of micro condensation that exists in the vapor form. And then the hydrogen peroxide will eventually decompose or disproportionate into water and oxygen gas, and that can be facilitated by the use of a catalyst. So putting those elements together, and if we distill the fundamentals from Annex 1, and this is one of the reasons for this series of webinars, is that decontamination should be automated, and we can also add in it should be reproducible. It should be validated or qualified in some way, and it should be of a sporicidal nature, able to show efficacy against a resistant microorganism. Isolators also decrease human interaction on setup. They take people away from grade A. They also have opportunities for automation and robotics. And if we're handling certain materials, we have the opportunity for containment as well. Okay, so we're going to have a look at qualifying an isolator, and the model used is one for sterility testing, but generally the principles are the same for aseptic processing isolators as well. It's just that some of the photographs and a couple of the nuances in here are sort of more deemed towards sterility, but it doesn't take away from the general principles that we'll be discussing. So we're going to have a look at the important operational criteria for the isolator. And to contextualize the operational criteria, we're going to have a look at some of the aspects of how the isolator can be qualified and how it should be maintained. And the isolators we're looking at is this kind of combination of two solid wall, it's called type 1 positive pressure isolators, and they're connected together by a rapid gassing port. So the objective of the gassing port is that it gives a smaller space for the decontamination of items, which can then be passed into bigger isolators, which can only need to be decontaminated at a lower frequency, say once a week, provided that the grade A conditions are maintained. And there's also, as part of the setup, a gas generator as well. So here's an illustration of the isolators that we're looking at. So we've got these two isolators with a decontamination chamber in the middle, and out of sight is a gas generator to produce the hydrogen peroxide vapor. So we begin by looking at isolator decontamination cycles, and it's important to have a look at these steps prior to discussing the validation and operational requirements of the isolator itself. So the first thing that needs to happen with any isolator is that items need to be loaded into the isolator, and it's important here that items are sterile. So certainly any direct product contact items and any indirect product contact items, as defined by Annex 1, are sterile items. and they need to be presented wrapped and then unwrapped. Some people also elect to undertake an additional manual disinfection of those items. That's not necessarily necessary, but it's something to consider. It's also important that the isolator that's being loaded, as I mentioned, is clean, and cleanliness is something else that needs qualifying, so cleaning validation studies, because otherwise the general assessment rests on an examination of freedom from visible contamination, but soiling will adversely affect the efficacy of the cycle. So in this particular case, we're looking at this mini isolator, or this gassing port. So it's a chamber connected to the isolator via interlocking doors. And so it can be loaded in itself without compromising the integrity of the isolators, and then also items can be passed through into the isolator once they've been decontaminated, again without breaking the barrier. So this would be connected to the gas generator, and the function of the gas generator is to take a defined volume of liquid hydrogen peroxide and then to heat that peroxide in order to produce a vapor, and to pass that into the chamber using sterile compressed air via a distribution nozzle. And it's important then that whether we're talking about the bigger isolator or the mini isolator, that the distribution of the hydrogen peroxide vapor is undertaken using some form of rotating nozzle, and then also distributed through the use of fans, because we need to make sure that the hydrogen peroxide vapor is reaching every nook and cranny within the isolator. There shouldn't be any part that isn't reached, and we would then qualify that, as you should see, through biological and chemical indicators. So this makes the presentation of items, the load, really important. So we need to make sure that items are ideally hanging, so we can get complete distribution around. So if we were to lay items onto a surface, then it would be very difficult. Or if we do need to use restings on surfaces, that they're surfaces with holes, as shown in the picture, so we get a good chance of distribution of the hydrogen peroxide. But occluded surfaces are a weakness and an area where we probably are not going to get exposure to the decontamination agent, and we may get failed cycles. So our cycle uses, as I mentioned, typically 35% concentration of hydrogen peroxide. And as the vapor is transported into the chamber, the isolator, to be bio-decontaminated, it's done so in sterile compressed air, which acts as a heated carrier gas. And we need the circulation of the vapor, and we also need to remove the hydrogen peroxide at the end. We can't wait for natural decay, because that would take a huge amount of time, but we need to aerate the isolator and bring down that level of trace level of hydrogen peroxide down to an occupationally safe exposure level. So the way that the hydrogen peroxide undertakes the decontamination, it's typically a form of microcondensation. There are different technologies. One group of technologies is slightly wetter, and one group of technologies is slightly drier. And there is obviously debate about the relative efficacy of those two technologies, but most literature indicates that they are fairly identical and appear equally efficacious. There is also on the market ionized hydrogen peroxide, which uses a lower concentration of hydrogen peroxide, so it's sort of down to sort of like 10% concentration. I have used ionized hydrogen peroxide. I have struggled with it, but I'm sure there are good technologies out there, but I did find it less easy, less reproducible than higher concentrations of vapor hydrogen peroxide. And the active kill is quite important, and it's about making that contact. It's that mechanism of imparting the hydrogen peroxide molecules to all exposed surfaces and being able to interact and to penetrate the microbial cell wall. We should never really forget those fundamentals. So different hydrogen peroxide technologies work slightly differently. So this is an illustrative one of a slightly wet process. And here there are 4 key steps to ensure the optimal hydrogen peroxide vapor disinfection process happens. So we have the vaporization of liquid to small molecules in the vapor phase for delivery of the target volume. We need to ensure we have development of the appropriate concentration of the vapor in the target environment to reach the appropriate concentration, and then to hold that for the appropriate time. And in this particular process, we're seeking saturated vapor conditions so that the gas concentration is at a point when it can hold no more molecules, and this starts a process of condensation formation, and the disinfectant agent surface deposition starts. This is in the process of nuclei forming on the outer surface of vegetative bacteria and spores, leading to a point of full coverage, the formation of a disinfectant monolayer around the organism, and then ideally penetration. And then obviously we need to get the hydrogen peroxide out of the isolator. Now, it's important that we control temperature and humidity, because the getting the vapor to the optimal conditions is robust when it's perfect, but can be fragile if it's slightly out. So it's important that we dehumidify the ambient air. So we're undergoing a initial conditioning process. So we need to make sure that the space within inside the isolator, the initial temperature and humidity in this space is optimized before we undergo vapor injection. So to achieve this, we'll have hot, dry air being exchanged with the target environment to achieve the required starting conditions. And then when we've achieved that, then we will start putting hydrogen peroxide vapor into the isolator, and we'll keep feeding that in until we hit a desired concentration, and then we can then start to achieve the whole time, the dwell time that we are seeking to achieve. And all of this needs to be optimized in terms of the how the gas generator achieves that concentration, how we set the gas pump speed, and how well we time the process and achieve the right conditions, and then undertake the appropriate circulation of the hydrogen peroxide, and then how we array and bring down to a level of below 1 part per million, which is generally the threshold of what's deemed to be an occupationally safe level. So the variables that we need to control are obviously starting relative humidity, surface and environmental temperatures, gas distribution and homogeneity. We need to measure the amount of evaporated hydrogen peroxide solution dosed into the target volume, because that's our measure of when we reach saturated vapor conditions, and gives a degree of assurance that we provided a sufficient monolayer of the disinfectant. But there's also going to be a variable with the types of materials that we use to construct the isolator, and also the types of materials that are going into the isolator. So we need to understand the load patterns and load configurations and the shapes and dimensions, and obviously the more things we put in, then the longer that cycle is going to take. Another factor is with relative absorbency of materials. So some materials can absorb different amounts of hydrogen peroxide. And the issue here is that if they then have a slow release process, this can increase the aeration time. So we can complete our kill roughly the same based on the mass and dimensions of materials, but our ability to get to the occupationally safe exposure level will also depend upon the nature of the materials and their absorbency. So if they are slowly releasing peroxide, it may take longer to aerate, so that's something else to consider. And isolators are often challenging to qualify, or when you come to requalify, what appeared to work no longer works, or something else may go wrong. And some of the things that can affect this are the homogeneity and the distribution of the hydrogen peroxide, and whether we're consistently distributing it. So, we might have initial distribution, but we've got to keep distributing that for our required length of contact time. So if we want to achieve a contact time of 20 minutes, we need to consistently keep distributing that hydrogen peroxide for 20 minutes. So if we have an uneven enrichment of our hydrogen peroxide vapor, then we may get microbial survivors. So we need this homogeneity, this uniformity. We also need to understand where we might have weaknesses and appropriately configure the fans and so on. And also understand that different materials may take longer to decontaminate than others. And also, if we've got movable parts as well, we also need to make sure that we can all parts will be exposed. So we don't want to have dead zones around conveyor belts, for example, and that sort of thing. Okay, so if we now have a look at some of the validation aspects. So the decontamination cycle needs to be validated or qualified, and this would be once we've worked out all the variables, a combination of chemical and biological indicators. And generally we'd use more chemical indicators than we would use biological indicators, because chemical indicators would allow that kind of mapping process. But we need to make sure that we're using a sufficient number of biological indicators in key locations. So for hydrogen peroxide, the biological indicator of choice is the same as we would use in moist heat sterilization validation, so for an autoclave, for example. And these are Geobacillus stereothermophilus spores dried onto stainless steel discs. And it's really important that we're using an inert carrier. Now, there is some debate about whether the discs should or should not be in Tyvek pouches. So the advantage of Tyvek pouches is that it facilitates the placement and helps against the cross-contamination, but the presence of Tyvek, which is a form of polyethylene fibre, can also create an additional barrier. So that there's a choice to be made, and that there's two schools of thought on that. It's also important that we can prove that the biological indicator is capable of germinating under defined conditions. So we must have a control that's not exposed to the isolator cycle, and that we're sourcing our biological indicator from a traceable culture collection, such as the American type culture collection, and that we have a sufficient concentration of spores at around 1 million, and that these are, as far as we can, create a even layer of those spores, and we're not overlaying the spores or anything like that. The death of these microorganisms, as we can demonstrate through fractional negative studies, is the same as with any heat process, so it's a logarithmic reduction. So also when we're using biological indicators, it's important that they're fully exposed. So again, if we were using, say, paper strip biological indicators in little glassine envelopes, that again makes them, one, slightly less representative of the isolated surfaces, but also there are risks of not getting full exposure, and we can then get failures when they're not necessarily really failures. There are so the culture conditions are important for standard biological indicators. So because it's a thermophilic organism, we need to incubate those biological indicators at 55 to 60 degrees. The standard time is 7 days. Some elect to go longer in case of slightly damaged spores, but pharmacopoeia minimum is 7 days. There are now coming onto the marketplace enzymatic indicators, and these can provide a rapid time to result, and literature suggests that they have good equivalency to the classic biological indicator. So I'd mentioned earlier about the importance of developing load patterns, and during the operational qualification and performance qualification, it's important that we understand the different load combinations, we understand the differences between them, and we can assess worst case whether every single load combination needs to be tested or some kind of matrix approach is adopted. It produced the same considerations when we're looking at autoclaves, and some would elect to do everything, some would elect to go down the matrix route, some would do minimum maximum, for example. But we need some form of rationale to decide how we're going to approach that, and the magic rule of validation applies in that we should be repeating that at least 3 times, and maybe more often in the case of isolators, because they're not quite as reproducible or repeatable as something like an autoclave is. But again, that's going to be a matter for your internal company policy. It's also useful to understand the point between pass and fail. So this can be full-blown fractional negative studies, or it can be assessing just between the point of passing and point of failing, and then building in a sufficient overkill cycle as well. And understanding where pass and fail happens, I think is really useful knowledge. If we just ran things that says, well, we know that works, we don't really then understand how close or far away we are from passing or failing, and then if certain variables happen, fans slow down, objects aren't quite placed correctly, we can then have problems. There's then a sort of general practice of, particularly with hydrogen peroxide and isolators, of using duplicate or even triplicate biological indicators, whereas with a steam sterilization device, we would tend to go for one biological indicator in one location. And this goes back to when biological indicators for isolators were less consistently produced, and the rogue biological indicator phenomena was more common. These days, biological indicators are made more consistently. There can be advantages to still going down the duplicate or triplicate route in the event of a single failure. There are mathematical calculations that can be done to show you're still getting log reduction efficiency, but equally there is a growing trend amongst some regulators that really the rogue phenomenon isn't really something that exists, and there's a bit of a debate there. There isn't unfortunately time to go into that, but again, it's an important choice to be made during the qualification. Another choice that needs to be made is the frequency of isolator load requalification, and then which load patterns are going to be repeated, but generally at least an annual requalification is important. Okay, so there's some other things that need to be considered and built into a rationale. So the first is the frequency of decontamination of an isolator. So for aseptic processing, this can be done for every batch, or it can be done for a series of batches that form a campaign. For sterility testing, it would depend upon the mechanism of transferring items into the isolator. So if we have the separate gassing port concept and we're transferring in, we may be able to do the main isolator once a week. If we're loading everything into one compact isolator, then we might be able to do that. We might do that each time. And all those kind of choices are going to come down to the degree of confidence, the degree of maintaining integrity, and how long cycles take as well, and how that fits into production or laboratory work streams. We also need to look at all of the environmental parameters and the environmental monitoring data, and to see how that is trending, and that can also be influential. So if we're getting slight drops in pressure, or we're getting occasional microbial recoveries, which is something that tends to be pretty unusual within an isolator. Another factor can be things like glove integrity failures or suspect failures and the rate of those, because although most glove materials are resistant to hydrogen peroxide, repeat exposure to hydrogen peroxide will eventually weaken most glove materials. I mentioned earlier about cleaning isolators, so it's important that we're regularly cleaning, and especially prior to decontamination, and we're using detergents and disinfectants that are not going to be overly aggressive to the isolator material, and which are not going to cause scratching or rouging. And certainly if we get scratches, then we're creating reservoirs in which spores can be deposited, and we may get microbial survival. It's also important if we're using hydrogen peroxide not to use a chlorine-based disinfectant, or if we do use a chlorine-based disinfectant, then we're really making sure that all the residues have been removed, because you can get quite horrendous reactions between chlorine residues and hydrogen peroxide residues. And the result of that will be that particularly stainless steel will start to get brown pitting on it. I mentioned the glove changes and how often gloves should be changed. I mean, the primary thing here is that gloves should be regularly subjected to integrity testing, and Annex 1 is signaling for aseptic processing isolators to undertake that assessment before and after each batch, and a similar principle should apply with sterility testing. How often gloves should be changed is something that is increased over time. So if it's a new isolator, we'll probably start with a relatively high change frequency, then start extending that out, looking at the data, looking at the integrity test results. And that's going to be partly based on the material. And with materials, there's always a trade-off between dexterity and degree of robustness. Environmental monitoring applies. I'm not going to say too much about this, but under Annex 1, it is no different. Just because there are enhanced protections from an isolator, the level of environmental monitoring needs to be equivalent as we would apply to a RABS or any kind of conventional clean room model. But it is important that we can demonstrate that the mechanism for getting media into the isolator is not going to be adversely affected by the hydrogen peroxide. So studies to show the suitability of the culture media to hydrogen peroxide, or if there was a micro crack in the bag holding plates, for example, if any peroxide got in, then it's not going to prevent microorganisms from growing. We also need to ensure that the room in which the isolator is held is also under a state of control, and this will be a clean room, either of grade D, perhaps for sterility testing, or grade C for aseptic processing isolators. And we want to make sure that that is well controlled, and we're not adding an undue bioburden into the isolator, and we're not tracking spores or fungi in, and that operators are appropriately gowned, and that the environmental conditions of the room are consistent, and they themselves are not going to adversely affect the isolator when we're running the cycle. So we don't want extremes of temperature or humidity in the room to adversely affect the isolator cycle. Okay, so just to kind of wrap up, there are some important parameters that we need to understand and monitor to make sure the isolator is operating correctly. So it's really useful to trend things like the volume of hydrogen peroxide used, the gas concentration, the alarm statuses during the cycle, the gas injection phase time, the humidity at the start of gassing, and trending those and looking for any drops in those can relatively early give us an idea of an isolator that isn't necessarily functioning correctly. So this is with an illustrative example. Every isolator is different. This particular isolator, which goes back to the ones we looked at earlier, required gas injection temperature to be between 41 and 50 degrees Celsius. And that is a key parameter for how well the vapor operates. The temperature inside as well was really important, as was the humidity. So we need to understand all of those to show that we can get a consistent and reproducible cycle. Similarly, with the gassing time, we would have established in a validation study that the gassing time needs to be so many minutes to so many seconds, and we need to make sure that we're not slipping below that during our routine operations, because that's a sign that we may not be getting the required level of microbial kill, and it also may signal operational issues with the isolator. So we might say that the peristaltic pump, for example, needs changing. Pressure, as I mentioned right at the beginning, needs assessing, and if we are getting drops in pressure, then we are getting the risk of air from the outside ingressing into the isolator. And we not only need to monitor the pressure, but we need to undertake regular leak testing of the isolator, and it would be conventional to do that prior to running a decontamination cycle. And we also need to ensure that our HEPA filters are running correctly, which you're going to mention at the beginning. And if we are requiring unidirectional airflow, which tends to be typical for an aseptic processing isolator, but less typical for a sterility testing isolator. But that's an important concept and an important contamination control principle. It's also useful, and my sort of final comment is that we need to undertake risk assessments of the isolator, and we need to look at all the different elements and undertake activities like failure modes and effect analysis, and we can score the different risks. And on this illustrative slide here, you can see that gloves, as I mentioned right at the beginning, are one of the kind of fundamental biggest risks. So that was a whirlwind run through the world of isolators. So we've looked at an introduction to isolators, decontamination cycles, biological indicators, some of the validation concepts, some of the key operational decisions, and some of the maintenance aspects. So thank you very much. I'll hand you back to Annette.
Thank you, Tim. Just while we swap over, we've had quite a few questions come in. So if I'll put my screen back on, and there we go. So the first one I have is from Nasir, and he said, for a lab isolator in a microbiology lab, do you need to perform a smoke study?
It's not mandatory, but I think it can be useful to kind of know how the active sterility testing influences the pattern of air, because if you can iron out or at least see that you're not getting any risk of contamination hanging in the air, then if you were, say, to get a sterility test failure, then you do have some useful information to fall back on. So I think for something that's relatively straightforward and quick to do, it can be useful, and then perhaps to repeat that if and when you need to change the fans in the isolator.
Okay, we've got a couple of questions about the VHP gassing. So Richard asked, would the recommendation be to test occluded areas with a sporicide prior to VHP gassing?
That can be done, I think, as like a final fallback. I mean, the key thing is to eliminate occluded areas as much as possible in the design. But if you can't completely, and there is a minor, so you've got a risk, then yes, I mean, your only recourse then is to go with a sporicide.
Okay, and Raghu wanted to know what was the recommended percentage VHP concentration solution for a bio-decontamination?
Okay, so the current, I mean, it depends on the agent that's used. So if we take hydrogen peroxide as the most common, so hydrogen peroxide is either present in the ionized form, for which you can get away with something like 10%, in the vapor form, whether it's the kind of wet or dry process, then the industry standard is 35% concentration. A few years ago, it was 30%, but that kind of got moved upwards to 35%.
Okay, I've also got a couple around the gloves. I've got Christian who said, where leak tests are performed on isolator gloves, what level of sensitivity should be achieved? And he was on about the size of hole detected.
Oh, this is a whole area of discussion. So the glove leak testers will go all the way down to pinhole size leaks, and there's two different types on the market. The most common one is one that inflates the glove and looks for pressure decay. There's been a lot of studies that say, okay, if you get a leak failure, it may or may not matter. It then really depends whether you can see the hole or not, because there's at least 2 papers out there where people have done experiments where they've got in with gloved hands with really high levels of Bravundomonas diminuta bacteria on their hands, had pinhole leaks, and nothing has passed through. So it's difficult to answer this succinctly. What's probably best is we use this one. I'll write a fuller answer when we do the written Q&A.
No problem. So possibly just one more question then, and so Paul asked, what is the main cause of glove leak failures?
It's either it can either be poor design, it can be poor choice of materials, it can be the sterilization process, it can be not changing them frequently enough and subjecting to repeated hydrogen peroxide things, and it can be sometimes the devices used to extend the gloves for the decontamination cycle to get full exposed surfaces, or it can be the things that they come into contact with. But generally, a good choice of material and a reasoned approach for the frequency of changing them generally guards against these issues.
Okay, I think that's all we've got time for now. Tim, I'd like to personally thank you for a wonderful series that we've done this year on the Annex one. I'm sure everybody that's attended have got nuggets to help them comply with it when it comes out in August, isn't it? It comes out.
Yes, it is.
Yeah, so, and I'd also like to thank everybody out there for attending. I hope you've also found it useful. We've appreciated all the questions you've asked, and the questions from today that haven't been answered while we've been on the webinar, I'll take to Tim and we'll send them through with a copy of the slides, probably in the next week or two. Please keep an eye on our LinkedIn feed and our website, where you might catch any of our previous webinars. You can download, or you might be able to see some of Tim's blogs or regulatory updates. Lots of very important information you can pick up there. We hope to have some more webinars for you, so keep an eye out for those, for any future webinars. As I said, this is the final one in this series, so thank you all for attending. I hope you've all found it as interesting as I have. Sorry, I forgot to move on my slides here. Here's a few training and support we can help you with. And I'm Annette Russell. I'd like to thank you all for attending, and hopefully we'll see you in the future.
Thank you very much.